Hi friends, in this video we are going to learn about types of sampling. In the previous video we have seen what is sampling theorem and the mathematical analysis of sampling theorem and the waveforms related to sampling theorem. So here we see the basic types of sampling theorem. There are three types of sampling. One is ideal sampling. Next one is flat top sampling. Next one is natural sampling. Okay. Now, whatever we considered in sampling theorem, the train of pulses, this was our carrier signal. So, whenever we do sampling using train of pulses, okay, then that type of sampling is called ideal sampling. Okay. So actually, what is an impulse? How can we denote an impulse? If we consider a box, okay, if we consider a box from 0 to A or 0 to T with an amplitude of A, if this T is tending to 0, if T is tending to 0, then I will get an impulse of amplitude A at origin, right? So instead of box, if I use my pulses as carrier signal during sampling, then it is called ideal sampling. Next is natural sampling. Okay. If my message signal is this and my carrier has squares, boxes. Okay. After sampling, if my amplitude of the carrier is changing with respect to message signal, then it is called natural sampling. If my amplitude of the carrier is changing, now you can see we have different amplitudes here. Okay, if it is changing in this way, it is called natural sampling. Then next is flat top sampling. Same case, my message signal is this, my carrier is this, right? Then after sampling, if this is my message signal, but my amplitude does not change. With respect to message signal. Now you can see here, my amplitude is remaining constant at all the intervals of time. This type of sampling is called flat top sampling. Okay. Now, the major effect we encounter during this type of sampling is aperture effect. Aperture effect. So what is aperture effect? Now, whenever we use these rectangular signals or boxes, the box signal as a carrier, then depending upon the width of the box, the sampling depends on the width of the box. So suppose now we all know that what is Fourier transform of x of a t? It is 1 by a x of omega by a, right? So whenever I am multiplying my time with a amplitude A in the frequency domain, I am dividing it with A. That means whenever I am expanding in time domain, it leads to compression in frequency domain, right? Whenever I am expanding in time domain, it is compression in frequency domain. So now if I use my x of t with a rectangle, it's a box signal or rectangle signal, rectangular pulse, okay, with higher width in time domain. So x of omega is frequency bandwidth of lower value. That means if I use this much width, then my output will be compressed, right? If you use lower width, then my output can be expanded. Okay, so aperture effect means whenever I use more width, then my attenuation will be more, right? So whenever I use more width, what happens in frequency domain? Only low frequencies can be retrieved and higher frequency components are all attenuated. Suppose whenever I use low width of rectangle pulse here, then I can retrieve the high frequency signals also. That means my attenuation will be lower. This effect, which is causing due to the width of the carrier signal we are using for sampling and change in the output signal, is called aperture effect, right? This is all about types of sampling and what is an aperture effect. That's all for this video. Thank you.